Hello, everyone. This is Coach White. I'm going to go through some of the questions that you guys have had and some of the formulas for Unit 11. So this is a lot of like interest and exponential and logs. So I'm going to go through a couple of those. Also, please mind my voice. I'm still recovering from our track meet. So let's go ahead and start with a couple things. So the first thing I want to talk about is some formulas. These are not all of them, but this is some of them. So here's our compound interest right here. So this is like our total, so the amount, and this is our principal, so the starting amount, and then 1 plus r, the rate, make sure it's in decimal form. N is the number of times that it is compounded per year. So if it's annually, n is going to be 1. If it's semi-annually, n is going to be 2. If it's yearly or daily, n is going to be 365, okay? And t is the time that passes. Now, if you have a continuous growth or a continuous interest, it is happening on the dot, like second by second. So that means we're going to use PE to the RT. I like to think about this as PERT. I know it sounds weird, but that's how I remember it. Again, we have the principal. This is E. So this is the value in your calculator. Please do not round it. Like we know that E is close to 2.71-ish, but please don't round it. Put E into the calculator, your rate as a decimal, and then your time. If you are solving for anything, do not give an answer or simplify until the very end, okay? This is like our geometric sequence. So this is the term that we're looking for. G of 1 is the geometric first term that you're given. R is the rate, which it happens. So if your number is doubling, then this would be 2. And then this is the placeholder, and then minus 1. So an example of this would be, let's say I start with a penny. Okay, that's 1 cent. That's going to be my G of 1. Okay. Now, if I say every week my penny is doubling, okay, so then my rate would be 2. And I would say, how much would I have after 7 years? I could do 7 minus 1. Okay, that's an example of one thing that you could do. So just to keep that in mind. The other big thing is coming down to your log and exponential. So this is red right here, log base b, so log of base b of y equals x. And this is b to the x equals y. One way that I like to remember this formula, okay, so I'm going to write it down again. Log base b of y is equal to x. I like to think about the b coming under the y and it's equal to x. So what's happening is, let me see if I can visually show you what's going on, okay? So this b right here is going to slide underneath the x, okay? And then that is equal to y. I know that looks a little weird, so it's basically like this. So the b slides under the x. That's where this comes from, okay? Please make sure you know how to go between the two because you're going to have to convert a lot. The other thing, too, is please make sure to know these two. If you see a question that just says log of x is equal to 10, you need to assume that the base is 10, okay? This is one of our natural logs, or common base of 10. This is not solving for anything right here. I am just telling you that log 10 of x is the same thing as log x. It's kind of like me saying 1x is equal to 1. Or I'm sorry, 1x is equal to x. They are the same thing, except you don't necessarily need the 1. It's the same thing over here. Log base 10 of x, you don't necessarily need the 10. It's implied. Okay, so they mean the same thing. Over here, this is different, okay? This is a log of e. Or I'm sorry, not log of e. Let me get rid of this real quick. This right here is actually going to be ln of e. You will usually see it like this, okay? So if it says ln of x is equal to 10, we need to know that the base is going to be e. So this would be e to the 10th is equal to x. Okay, it's just something that's implied. It's just not written. ln is on your calculator. It is like the third button up from the on button. And log is also on there. I think it's the fourth button up from the on button. Just make sure you know those, okay? Now, a couple other things too. Identify the characteristics of a graph based on this function. The very first thing that I would do here is I would maybe do your transformation table, okay? So the very first thing that we need to do is we need to do the parent function, so k of x, okay? When you use your points, always use -1, 0, and 1. It just makes things so much easier. Now, the way that you figure out the parent function is all you do is take this base and raise it to the x. So that means my parent function over here, and I'm just going to write it so you see it. My parent function is going to be k of x is equal to 5 to the x. That's my parent function. It's just the base raised to the x, okay? Once I do that, I just need to plug things in. So I'm going to come over here and I'm going to be like, okay, 5 to the negative 1 is what? That is just 1/5. 5 to the 0, anything to the 0 power is going to be 1, and then 5 to the first is going to be 5. So those are my starting points. Now I'm going to go over here and I'm going to do the transformations, okay? So I noticed right here, this is telling me that x is going to the right 1, or right 3. And if I come over here, I see that there's going to be a Roya, and it's going to be a negative 2y. So that is now going to be my transformed function, okay? Oh, and please don't forget when you're doing these, so the asymptote for any exponential function is going to be y equals 0. Okay, that's our asymptote. So I come over here and I'm going to fill this in, and I'm going to do negative 1 plus 3. So negative 1 plus 3 is just going to give me 2. And then 0 plus 3 is going to give me 3, and then 1 plus 3 is going to give me 4. Now what I'm going to do is I'm going to do 1/5 times negative 2. I'm just plugging it in. So that's going to be negative 2 over 5. Go ahead and leave it as a fraction. 1, so negative 2 times 1 is going to give me negative 2. And then 5 times negative 2 is going to be me negative 10. Okay, so there's where I'm at. Oh, and also I need to do my y, my other asymptote. Negative 2 times 0 is just going to be 0. I also know that the asymptote's not going to change because there's no k value here. It doesn't shift up or down. So on the transformed graph, it's going to be y equals 0. Okay. And then I need to go ahead and find my intercepts. The best way to find this intercept is that I need to plug in 0 for x, okay? So I'm going to go over here and I'm going to do k of 0 is equal to, and I'm using this function right here, negative 2 times 5, 0 minus 3, okay? And this becomes negative 2. This right here is going to be 5 to the negative third, okay? 5 to the negative third, I'm going to do it over here. 5 to the negative, 5 to the negative third is the same as 5 over 5 to the third, okay? That's with our exponent rules. So this becomes times 1 over 125. Okay. So my final answer for this intercept, and I'm just going to erase this a little bit, so make sure you have it copied down. Okay, I'm going to zoom in. So that means my y-intercept here is going to be 0, and then it's going to be negative 2 over 125. That's going to be my intercept. And then my end behavior, if I'm going to graph this, I'm going to go ahead and I'm just going to pull this off to the side real quick. So bear with me, it might be a little messy. Okay, so I'm just going to pull this down here. If I have my graph, okay, based on my transformation table, I need to go over 3 for the x, okay? I still know that my asymptote right here is at y equals 0. So y equals 0. Okay. I know my intercept is going to be at 0, negative 2, 125. So that is, if this right here is negative 1, I know it's going to be like way up here. Okay. And I know there's a roxa. So that means my line is going to look something like this, and it's going to go down. Okay. So my end behavior is as x goes to negative infinity, y is going to 0, because we see I didn't do the best job here. So this is going to go down. This is actually approaching the asymptote. So it's approaching 0. That's what's happening there. And then as x goes to infinity, you guessed it, it's going down all the way. So y is going to negative infinity. So it's going all the way down. Okay. Those are the biggest things I want to talk about. Also, this graph is going down. Please do not be mistaken. We look at the base. If the base is bigger than 1, it is going to be growth. So please, I know this is going down. It is not decay. The base is bigger than 1, so it's going to be growth. Okay. Now, another thing that I want to talk about here is draw a graph of an inverse function just based on this. Okay, and finding the inverse. So this is the original function. One thing I want you to keep in mind, when there is no transformations, there's no left and right, no up and down, you are going to have 0, 1 on the graph right here. The reason for that is if I have like y equals 5 to the x, 5 to the 0 is just going to be 1. If I had y equals 100 to the x, 100 to the 0 is just going to be 1. So that's why if there is no up and down, left or right transformations, this point is going to be on the graph. Okay. Now, the other thing, too, that we have to keep in mind is if you look at 1 comma b, that's going to tell you your base. So if I come over to this graph, I'm going to go over and I'm going to go over 1, and I see where that point's at. So this point right here is at 1 comma 2. This is telling me my base. Okay, so my base is going to be 2. And there's no left or right. There's no up and down. 0, 1 is on there, and my asymptote right here is still y equals 0. So that means my equation for this function right here, oh, I'm so sorry. My equation for this function right here, so f of x is going to be equal to 2 to the x. Okay? Now, when we solve for the inverse, which is what we need to do down here, write an equation of the function that is an inverse, I need to take, so I'm going to take f of x, and in this case, what I'm going to do is I'm going to make this a little bit easier. Okay, so I'm going to change this to y. Y equals 2 to the x. When we find an inverse, we need to swap x and y, so 2 to the y. Now remember, we need to do our exponent rules here. Okay, so with our exponent rules, or exponent to log if you need to look back in your notes for the formulas right here. Okay, so we know our 2 is going to be the base. So log 2. Okay, so I'll just do this. Base is 2. Our x value, so if we want to come back over to our equation, okay, so we notice here that our x is going to be the exponent. Okay, so I come over here, and the exponent is y, and the y value is going to be x. I know it's a little bit confusing. I mean, it's just what we're working with right here. Okay, so then to write the log, remember it's going to be log b of y is equal to x. So log b is 2. I said that y was equal to x. Okay, and I already know that my x is equal to y, which is perfect. That's what this is right here. So the function for my inverse when I'm writing this is f inverse of x is equal to log base 2 of x. Okay, that'd be my inverse. Now, when you are plotting it, your domain and your range are going to change and your points are going to change. So this one right here is 0, 1. And they're just going to change. So it's going to be 1, 0. So it's going to go right here. This point right here is 1, 2. So it's just going to swap. It's going to be 2, 1. So right here. And remember, when it reflects, it is reflecting over y equals x. So right here, this is y equals x. So it's reflecting from this side to this side. So my line right here is relatively going to look like this. Okay, that would be my inverse. And it says, what are the asymptotes? Well, for any exponential function like this, there's no shift up and down or left or right. So I already know that for f of x, that my asymptote, my horizontal asymptote is going to be at y equals 0, which we already have right here. And then for f inverse of x, things are going to change. Remember, we have to swap x and y. So now we have a vertical asymptote, but now it's x equals 0. Because again, we swap x and y when we have inverses. Okay. That would be a big thing here. The biggest thing is this. Please remember this. That's the best way to find what your base is. Okay, here's the other one I want to talk about real quick. Same thing. We want to look for sorry, that was kind of ugly. Let's do 1, b. If I zoom in here, I see that this point right here is like 1, 2.7 maybe. I want to remind you, the value of E is close to 2.71. This is extremely close. So that's telling me that this function right here is f of x is e to the x. Okay, that is one I would probably memorize. That would probably help. Okay. Now, when we have to write our inverse function, the inverse of e to the x, okay, this is another one that it would be smart to memorize. e to the x, the inverse is just going to be ln to the x. Okay, because remember, this is our base right here of e, but it's just not shown. Okay, so that's going to be our inverse. Again, these, I would memorize them. Okay, it just makes it easier for us. And also, here's a tidbit. If you go on your calculator and you see the button that says ln, like this, I believe, if you see the little blue lettering above it, I believe it says this. Those are inverses of each other. So if you ever forget, just look at this button on the calculator and the inverse is right above it. Same thing. If you see like the x squared on the calculator, right above it, it shows the square root. That's because they're inverses of each other. Keep that in mind. It's a little nice trick to know. Okay. And then we just need to find the asymptotes. So same as above on our last one. This point right here is at 0, 1. So I'm just going to go to 1, 0. This point right here, we already said was 1, 2.7. So I want to go to around 2.7 and up 1. Okay. This line is going to look a little bit like this. Okay. So I just want you to keep that in mind. It's going to look like that. Because we know that for f of x, we are going to have the same thing. We're going to have a horizontal asymptote of y equals 0. And then we're going to have a vertical asymptote of x equals 0 for f inverse of x. Also, I apologize. I need to fix this one right here. This graph is not accurate because I said my horizontal asymptote was at x equals 0. So I can't cross this line right here. So in fact, actually, this one would look more like this. I apologize about that. Okay. The other one, too, is determining whether each function represents exponential growth or decay. The biggest thing is if it's growth, your base is going to be greater than 1. And if it's decay, it's going to be between 0 and 1. Your base right here is not a transformation. Okay? Big time. It is not a transformation. The only thing that the base tells you is if it's growth or decay. That's it. So I'm going to come over here. And I see my base. Ooh, my base. And the base is what the exponent is raised to. This is greater than 1. This is going to be growth. Okay. Next one. Do not be fooled here. That is not the base. This is the base because it's 5 raised to the negative x. We can also write this as 6 times. So 5 to the negative x is going to be 1/5 to the x. Our base is a fraction between 0 and 1. This is going to be decay. This one, greater than 1, growth. This one, less than 1, decay. This one right here, please be careful. If it's to the negative x, that means they swap. So this is going to be 0.8. And if it's to the negative x, this is going to become 8/7 to the x. Therefore, this is growth. Okay? And lastly, we have a decimal that's in between 0 and 1, so this is going to be decay. Don't let the negative exponents fool you. Okay? And let's see. Okay, here's another one I wanted to talk about real quick. This is our half-life. We briefly talked about it. So when we have a formula for our half-life, the only thing that's going to be different is so we're going to have our a to the t. We're going to have our principal. It's a half-life, so the rate's already going to be 0.5. Then you're going to have your time that passes, and then the time of the half-life. Okay, so I'll describe this to you in a second. So it says at 8 a.m., the amount of caffeine in a person's body is 130 milligrams. This right here is going to be our P, okay, because that's the starting amount. The caffeine has a half-life of 2 hours. The 2 hours is going to be our 2 to the 1/2, or 2 subscript 1/2. This just means the half-life of that chemical. Okay, that's all that subscript means. So it says, write a function that describes the amount of caffeine in a person's body h hours after 8 a.m. Okay, so we're going to come over here, and we have our a to the h because it's asking us for h. We know our principal is going to be 130. We already know it's a half-life. So you can put 0.5, you can put 1/2, doesn't matter to me. Okay, we need to solve for h. And we already know the time of the half-life is going to be 2 hours, so we just put 2. Please make sure if you put this exponent into the calculator that it is done correctly, so it doesn't give you a weird number. This says to the nearest milligram, how much caffeine will be in a person's body at 11 a.m.? Okay, so this is our T. If they start at 8 a.m., how much time has passed? I don't know, Coach White, how much time has passed? Well, between 8 and 11 a.m., that's going to be 3 hours. That's some easy mental math right there. Okay, so then we just plug it in. So now we're going to have A, and we're plugging in 3, so 130, 0.5, and then we know our time is going to be 3, and then it's still over 2, okay? If you plug that into the calculator, okay, so your answer is going to be close to 45.96 milligrams. And again, that makes sense because this is the amount you start with, and as time goes by, that caffeine wears off, right? How many of you have had a Celsius or an Alani or Red Bull or whatever that is? Once you have the caffeine, it kicks in right away, but slowly over time, the caffeine wears off. So this makes sense. Caffeine's wearing off because it's less than 130. Okay. Those were the biggest things that I wanted to show you guys. Again, I would make sure you have your formulas memorized. I don't have the half-life one on here, but let me go ahead and add that real quick. So the half-life one is going to be A to the T is equal to P 0.5, and then we are going to have our time elapsed over the time of the half-life. So let me go ahead and write this down. This is going to be our half-life formula. Okay. So if you have any questions, please let me know. But those are the biggest concepts that I would know. Also, make sure you know how to write down formulas, not necessarily solve, but writing them. Another thing is knowing how to do transformations of logs. Please know, let's see if there's one on here. No, I don't necessarily see one. But please, please, please make sure you know how to do a transformation table. Okay, so that's the ones where maybe it gives you a formula like this and you need to do a transformation table. So a lot of the times it's going to be like you're going to have your parent function, okay, and you have to have your x and your y. And remember, it's usually going to be -1, 0, and 1. And then it's going to have your transformed function. And it's going to have your whatever your transformations are, okay? So again, if I'm just looking off this one right here, I know that it's nothing happens to x actually. I know that there's going to be a Roxa. I know it's going to go up 3, and my base function, so my base is 1/7, so this is decay, right? My parent function is going to be p of x is equal to 1/7 to the x. So again, that's what I would plug in here. So my transformations, nothing happens to x. I know there's going to be a -y because of a Roxa, and then up 3. And then I would fill it in and go ahead and graph it. Make sure you have to do end behavior, your asymptotes, and so forth. Okay? But yeah, if you need help, please just let me know. And hey, you got this. Good luck.